So this is practice problem 1. Sulfuric acid plus aluminum hydroxide, acid plus base gives you salt plus water. The salt is the aluminum sulfate, but you have to write it correctly like you write ionic compounds by switching their charges. So you can't just write Al as O4, you have to write Al2, parenthesis SO4, parenthesis 3. That's aluminum sulfate. Okay, so then are we balanced?
Well, I have a balance.
Well, I don't. Oh.
There's 3.
Here?
Mm-hmm. And there's a 2. No. And now we are.
No. Can't be. There's got to be something else.
Why?
Because if I get 6 H's and 6 OH's, how many waters am I going to make?
Oh. You're gonna make 6.
Did you say something?
I
Real loud.
Is it 3?
If you get, 6 H pluses from here, and you get 6 OH minuses from here, how many
you're
waters
gonna
do
get
you get?
6.
Okay. So does everyone follow that? We got 6 hydrogens donated from the acid. When this dissolves in water, it'll dissociate like ionics do, and you'll end up with 6 OHs. So 6 hydrogens plus 6 OHs gives you 6 waters.
I have a
Now we're
question.
balanced. Yes.
When you balance these, do you use the whole hydroxide as one, or do you split it up between oxygen and hydrogen?
I always think of hydroxide as a little family unit that sticks together. And so it becomes water. Like if you think of water as like hydrogen hydroxide, kind of, then it gets the 6 hydroxides, 2 times 3 hydroxides. It gets the 3 times 2 hydrogens, and you end up with 6. But if you want to count separately, that's fine too. What you don't want to do is think like 3 sulfurs, 12 oxygens, 3 sulfurs, 12 oxygens. You want to think 3 sulfates and 3 sulfates. The sulfates don't break up, so you can think of them as kind of one thing. And that makes it a lot faster to count. But you'll get to the same end either way. But if you find you can't balance it, the first thing you want to look at is, did I write the ionic compound right? Because if you write the ionic compound just like sloppily or wrong, tends to make it really hard to balance the equation. Then you're like, hey, wait, I think I did something wrong. So, any other questions? All right. So now we've got Grace. Give the balanced equation for nitric acid and calcium hydroxide. Nitric acid
HNO3.
and calcium hydroxide.
Ca parenthesis OH parenthesis 2.
Alright. And both of these behave kind of like kind of like an ionic thing. So you're going to make
Water, so H2O, and Ca parenthesis NO3 parenthesis 2.
Alright, so note that Grace wrote calcium nitrate correctly. She didn't just say CaNO3. She said, oh, Ca has a 2 plus charge, and NO3 has a 1 minus charge. So I have to write it correctly. Then we balance, or is it balanced?
There's a 2 in front of the first one, and a 2 in front of H12.
Okay. So then she has 2 hydrogens here for the 2 hydroxides here. That gives you 2 waters. And then 1 calcium and 2 nitrates. That works there. Can you see how hard it would be to balance if you hadn't written calcium nitrate correctly? Yes, so that's the first thing you want to think about if you're having trouble balancing is my salt written correctly? That's perfect. So, Kristen, given that ammonia, NH3, is a base, what is the reaction between ammonia and H2CO3, which, what do we call that?
Carbonic acid.
Yes. So, reaction between ammonia and carbonic acid So when you have a truly covalent acid or base, and in this case ammonia is a covalent base, you're going to produce what?
2 ions.
2 ions, and what are they?
Ammonia and carbonate.
So you produce the ammonium ion, NH4+, and the carbonate ion, CO3 2-. Both of those are ions you know. They're not ions you made up for convenience. So, are we balanced?
There's 2 in front of the first one, and 2 in front of the ammonia ion.
This. And that uses up 2 extras, so that's good. And notice that the charges remain balanced on both sides, right? Net neutral, net neutral. So that side is neutral. And this side, 2 positive charges, 2 negative charges, still neutral on the product side. So if you end up with your charges not balancing, that's also a problem. If you're neutral on one side, you have to be net neutral on the other side, Lily.
So where did the hydrogen in front of, on the front of carbonic acid, like there's 2 of those,
2 of them
and then we gave 1.
went to 2 of these guys.
So they both went.
Like 1 hydrogen went to 1 ammonia and 1 hydrogen went to the other ammonia. Once you balance, that's what fixes it. So you have to make ions you know and then balance.
Okay, so you make ions that you know out of what's on the reactant side, and you don't worry about like, oh, but there's 2 hydroxide molecules, what are they the second?
Right, what fixes that is balancing.
Okay.
And that is a tricky thing about these really, really covalent kinds of things. I inhaled like ammonium hydroxide smell. Okay. So, any questions about that one? That one's good. So Austin, when HBr is mixed with water, what reaction occurs? So, when we mix HBr with water, what is going to be the acid? What's going to be the base?
We know that water's the product, so water's going to be the base here.
Is HBr?
Yeah.
Okay. So if you have hydrobromic acid, it's definitely going to be the acid.
So the H is going to leave the hydrobromic acid and join the water, and we're going to have 2 ions. We're going to have the H3O positive, and then we're going to have bromine, which is negative.
Good. So we don't even have to do anything to balance it. That's perfect. Remember, if your acid or base is covalent, like your base in this case is, you make 2 ions. And the only 2 positive ions you know are ammonium and hydronium. So, did we do any more of these?
Nope.
No? Okay. So, we can try to get you ready for next week. Let's see. Let us look at my lesson plan and see if I have extra problems written on this week's. And if not, then we'll pull out some.
Can I go to the bathroom?
Sure. Well, I figure out what to do.
Can I go too?
Yes. Okay. So let's talk about concentration problems. I don't want to pick a super hard one at first. So let's actually just look at practice problem 5 together. And that one in a sec. I'm going to email extra practice sheets for 10. If you do them because you need more practice with 10, that's good. If you don't do them, I'm not going to check. But this is hard, and we use it every week from here on out, except for light week.
We have practice problems and extra practice problems.
And then my extra practice problems, and yeah. So I had to write a makeup test for somebody once, so I'm happy to have a whole sheet full of extra practice problems.
So are they mandatory, or if we want?
They're not mandatory, but you definitely want to master this stuff so that it's old hat, super easy. And you want to make every possible tricky mistake that there is to make before you take the actual test. Because if you get fooled on these, no problem, you just fix your mistake. If you get fooled on the test, that giant collection of 99s and 98s might go down to 90s. I love you guys. I love looking at my end grade for chemistry. So, it says give the concentration and molarity of each of these following solutions. So we've got 3.51 moles of HNO3, which is what? Nitric. And we want to dilute that up to 1.2 liters of total solution. SOLN means solution, because I don't write the word solution ever, and nobody else that I know does either. So if you see that, that's what it means. Okay, so how can I find concentration? So what units am I looking for when I'm trying to find a concentration? Okay, so I want to get concentration in capital M, which is mole over liter. For this, it's pretty easy. How do I do it? I know you did it below, so think for it. So if I need units of moles over liter, how can I find the concentration if I have moles and I have liters?
Divide 3.51, or, yeah, and then 1.2 on the bottom. And divide.
Okay. And then, if you type that into your calculator, what do you get and how many significant figures can you keep?
You would get 2.9.
Everybody type it. Find a calculator.
Dude, you can borrow mine.
It's okay, I can use my phone. We're not gonna square root anything today, I think, so we're good.
2.9.
I just don't like to, I mean, I guess the old 80s way of not using a phone in public. It's just a
I have an 80s calculator.
Ooh. We still have my husband's college calculator, which is hilarious. And I still have the calculator I used when I took physics in high school, but it's very similar to one I usually use. Except it has a button battery that pops right out, so I'm scared to really do it.
This is my mom's from high school.
Does it have a button battery that pops right out?
No, it's
Okay, good.
solid.
Oh, nice. Those are snazzy. Okay, so what did we get?
2.9.
Okay, so we can keep 2 and 2.9. And what will my unit be?
Molarity.
Molar. Yeah, molarity. So I would say 2.9 molar, and that capital M means moles per liter. And then always you have to put the name of the chemical. Even if Dr. Weil doesn't say so, I say so. If you don't put the name of the chemical, you're losing an eighth of a point. Label your stuff. It's important to me. And these are all. This was my mother's outfit, and I miss her and I love her. But I don't know how she got through the day with stuff falling off. So, then it gets a little more complicated. So the next problem, this is 5A if you went to the bathroom. 5B, I'm going to change color just so it's not confusing. Says you've got 234.1 grams of KOH. And you're going to make 345 milliliters of solution. I'm just going to write 345 mils over here because we can just do our math. So, to get concentration units in moles per liter, what do I need to do with these grams? Convert to moles. So how do I do that? She's looking over your periodic table. Yep. So, what's our molar mass of KOH? I'll give you all a minute for that. I'm going to leave this down.
I've done all my OIRs.
Yeah, you're probably right. I got one of the honor arms wrong from Ginny. That was a fun moment. So did everybody get the molar mass of potassium hydroxide? Is it 56.1?
Yeah.
And what would my unit be? So potassium is 39.1 grams per mole, oxygen 16.0, hydrogen 1.01. So, I get 56.1. So how can I, if my molar mass is 56.1 grams of KOH per mole, how can I use this to cancel out grams and get moles?
You divide 234.1 by 56.1.
Yes. So, if it's true that there's 56.1 grams of KOH in 1 mole, it's equally true that 1 mole has 56.1 grams in it. So, remember that molar mass is a conversion factor. You can just flip it right over. You'll be doing that like all the time now. So we cancel out our grams and we get moles. So, once you have moles, then how do you get moles per liter? So, a lot of people stop and round, and that's fine. If you do it that way, no problem. I don't usually. I just know I want moles in the numerator, liters in the denominator, so I just do it. And then if you do 234.1 divided by 56.1 divided by 0.345, hopefully, what do we
We'll get a
get?
slightly different answer if you don't round, right?
You might be like, but within the significant figure, the last digit, you should be right on. And I wouldn't mark you wrong if you round in the middle. But I don't know anybody who actually does round in the middle in chemistry ever. So probably you'll never see a professor like stop and round in the middle. They'll just regurgitate giant math onto board and hope that you keep up. What do we get? After everyone gets it, I'll get Micah to tell us if we're right. Oh, I think I got what you thought. Okay, what'd you get, Micah?
I got you. Are we talking about the final
It's
answer?
the final answer.
Okay, 12.1 molarity of potassium hydroxide.
Okay, 12.1 molar KOH. This is why we're glad there's no M as an element, or we'd be in trouble. He kept 3, which is good because it would be 3, so that's what I get. So if you take 234.1 grams of potassium hydroxide, and you dissolve it into 345 milliliters of water, this is the solution that you'll end up making. And that's good. do C on your own, and then we'll put it up, and then if we still have some time, I'll make up a problem. In fact, while you're doing C, I'll make up a problem. When you get done with C, then you start on the blue problem on the board.
Is there like an extra calculator I can have?
Oh, you can borrow mine.
Oh, we'll look and see that last one. You guys can share. So in the titration, your goal is to use up all the acid and all the base. So you have nothing left over. So neither is the limiting reactant. You use up both equivalent at the, you stop at the equivalence point basically. And that's what we're going to do in the lab next week.
Were we supposed to read how to do this?
No, I'm just trying to, this is just like
Somewhat
preview
lost.
of next week. Yes, I would expect everyone to be somewhat lost. This is just a preview of next week because it's such a large amount in this module to cover that if you have already seen a little bit, when you read it and do it, it will maybe be, if I break the brand new blinds, I would say, on camera especially. But titrating is something that requires a nice steady hand, so you'll have lab partners to tell you to slow down.